Good. Okay. Well, thanks for the invitation to speak. Um, I've been asked to give a sort of general overview of molecular spectroscopy with a particular emphasis on the mid-infrared. So the types of observations that have been done with the XES instrument on SOFIA. So what I thought I would do in what is going to be a 1 hour talk is start with an introduction to molecules in the universe, why we might be interested in them. And then I'll go and talk a little bit about the physics of molecules, how they interact with radiation, which is, of course, the only way we know anything about them in astrophysics, and discuss electronic, vibrational, and rotational transitions, 3 different ways that molecules can interact and emit or absorb radiation. I'll then talk a little bit about astronomical instrumentation for the mid-infrared. And here I'll mention the unique capabilities of the XES instrument. And then I'll finish with a couple of examples of mid-infrared spectra that were obtained with XES, and tell you about the wealth of information that they can provide if they are interpreted carefully. So that'll be the outline. So let me start right away with a discussion of molecules. So one of the key points that has always impressed me about the universe is that molecules are ubiquitous. We find them in a very wide variety of astrophysical environments, and we actually see a very wide range of different molecules. So the places we see molecules include the interstellar medium, the densest parts of which are, of course, the sites of star formation. We also see very rich molecular envelopes flowing out of the surroundings of evolved stars that have left the main sequence, where the surface gravity is low and the radiation pressure is high because of the very high luminosity. And these stars then can lose mass at a very substantial rate. They can't do it for long, of course. But while they do so, they're surrounded by a rich molecular envelope. Other environments where we see molecules include the comae that surround comets when they come close to the sun, and the mainly water ice starts to vaporize, releasing water and many other molecules into the surroundings. We also see molecules in the accretion disks that form during the formation of stars and planetary systems, and also on a much larger scale around the supermassive black holes at the centers of active galaxies. Molecules are found at very high redshift as well as locally. And they're also seen in stellar atmospheres, including the sun, in fact, in sunspots that are a little bit cooler than the rest of the sun. There's a detectable concentration of molecular hydrogen. And of course, in planetary atmospheres, and this, of course, now includes both the planets of our solar system as well as exoplanets, where molecules are a very important constituent and provide unique information about the atmosphere or the nature of the planets we see. There are actually, at this point, more than 250 molecules that have been detected in the first 2 environments, I'll say the interstellar medium and circumstellar outflows. And some of these are very familiar. You could find them in your kitchen, and some are very exotic. So here's a list from a compilation maintained at the University of Cologne. And the molecules here are just ordered by the number of atoms they contain. And you can see, some things you could literally find in your kitchen, at least in solid form, if not the gas phase: sodium chloride, water, carbon dioxide. Some of these are very stable molecules, and some are very reactive and really quite exotic. Most of these were discovered by radio telescopes through spectroscopy of the line spectra of rich radio sources, molecule-rich radio sources. And you can see that many of them are organic, particularly as one gets to larger and larger molecules. So there's just a huge inventory of molecules and a very interesting chemistry that leads to their formation and destruction that we would like to understand. And this gives actually a subfield called astrochemistry that has been of great interest to me and probably many other people who are speaking today. These molecules are important really for two reasons. The first is that they provide very valuable information as probes of the environment in which they're detected. And in particular, they provide unique information of general astrophysical interest that would be hard to get in any other way. So because they have a rich spectrum of rotational, vibrational, and electronic transitions, as I'll discuss in a minute, they provide, or the relative strengths of the different lines they emit and absorb, provide a very valuable probe of the excitation conditions, the temperature and density of the gas where we see them. Because we can detect these molecules, particularly in the radio millimeter and submillimeter at very high spectral resolution, particularly with heterodyne instruments, they're a very good probe of the kinematics of the gas through the Doppler shift. And then if we can understand the chemistry of the molecular clouds in which molecules are found, we can actually get a very good handle on two things that would be very hard to probe otherwise: the density of cosmic rays, which are an important source of ionization, and also of ultraviolet radiation. Another very useful probe that molecules provide is of isotopic abundances, because there's a very large isotope shift for molecules as compared to atoms, so that we can readily distinguish molecules containing different isotopes of the same element. And then, I believe you had an extensive discussion of magnetic fields yesterday. Molecules also probe magnetic fields because their energy levels respond to magnetic fields through the so-called Zeeman shift. So that's the first important reason for being interested in molecules. The other is that molecular emissions can actually dominate the cooling of the gas. So if we want to understand why certain environments have the temperature they do, we have to consider the balance between heating and cooling. And certainly in molecular clouds and in circumstellar envelopes, emission from molecules is the main way the gas can cool. Another interesting environment where theory tells us that molecules must be important coolants is in the early universe, where we only had hydrogen, helium, and lithium before the period when stars formed. And none of those elements is a very effective coolant in atomic form once the temperature drops below about 10,000 Kelvin. But if only a small fraction of molecular hydrogen forms, and we believe it does, then that would actually dominate the cooling that leads to the first galaxies and the first generation of stars. Okay, so that's sort of an overview of why we should be interested in molecules. We need to interpret the observations we make of molecules carefully to get the most information that we can out of the interpretation. And a good interpretation requires really a detailed understanding of the fundamental physical and chemical processes involved. That understanding can come from theory, but laboratory measurements also play a very important role. And together, those two things, theory and experiment, are referred to as laboratory astrophysics. So if you consider the subfield of molecular astrophysics that X's observations fall into in many cases, there are really three components in a tripod, if you like. We need laboratory astrophysics and related theory to give us the spectroscopic parameters we need, and various other parameters, the rate at which molecules would be excited in inelastic collisions, the rate at which they would react to form different molecules, the rate at which they're destroyed by photons, and how they react on the surfaces of dust grains. And then the second element is observations of astrophysical molecules, so measurements of emission line luminosities or absorption line optical depths. And then we also need detailed models for the objects that we're observing, whether they be diffuse interstellar clouds, dense clouds, circumstellar outflows, regions heated by interstellar shocks. And so by combining these three elements, the idea is, the hope is, that we can get information of general astrophysical interest. Okay, so that finishes up my introduction and motivation for this. I'm now ready to turn to the second part of the talk, which is how molecules interact with radiation. Before I do that, can I just check that you're seeing and understanding me clearly and seeing my screen? Maybe just one of the hosts could just confirm or suggest any changes here.
I'm seeing your screen clearly and hearing you very clearly as well, so there's no problem there.
And you're not wanting me to stop for questions during, they'll be at the end, is that right?
Yes, but well, maybe there's a short question now that is in the chat. If the interruption is not a problem.
Okay. Unfortunately, I can't see the chat while I'm in full screen. Would you be able to read it to me?
Absolutely. So is this a question from Arpita? She wants to ask, what do exotic molecules mean here? I missed that out.
Yeah, so by exotic, I mean, it's partly in the eye of the beholder, but I really mean molecules that are not well known to chemists and actually, right. So sort of unusual, quirky molecules that you might not have thought of when you think of the most common stable molecules. And actually, one of the interesting things is that some molecules were actually not known in the laboratory before they were discovered in interstellar space. And so one example would be the molecule C3H2, which has a cyclic form with 3 carbons in a ring and 2 hydrogen atoms. And it showed up as some unidentified spectral lines in the radio part of the spectrum, and only subsequently was made in the laboratory. And it was sort of a Sherlock Holmes sort of exercise to figure out exactly what molecule it was. So, you would look, and if I have a electric discharge in a gas containing certain components, I'll see these lines, otherwise not. And it was a complicated story to actually identify this molecule that previously was, in fact, not known to molecular physicists. Okay. So the first thing to say, I guess, is that molecules can exist in a variety of quantum states, and these are basically just solutions to the time-independent Schrödinger equation, the some wave function, where if you operate the Hamiltonian operator on that wave function, you get some multiple of the wave function itself. So the wave function is called the eigenstate, and the number here, E, is the energy of that state, the eigenvalue. So you have all these stationary states, and then you can have transitions between these states being accompanied by the absorption or emission of radiation. And depending on what the states are, that could be extremely slow, negligibly slow, or quite rapid, that transition. And to characterize one of these quantum states, well, they have different degrees of electronic excitation, vibrational excitation, and rotational excitation. So the electrons can be excited, and then in addition, or instead of that, the molecules can vibrate or rotate. One of the ways of representing this is shown in this figure, which refers to the hydrogen molecule. And these colored curves show us the energy that the molecule will have as a function of the separation of the two nuclei that is measured here in what's called atomic units. It means in multiples of the Bohr radius. And you can see most of these curves have a local minimum, which would be the equilibrium separation of the two nuclei. And the red curve represents the ground electronic state of the hydrogen molecule. So if you had two widely separated atoms, you'd be on the right part of this red curve. So that would be two atoms in the ground state. And then as you move them closer together, there's an attractive potential, and the energy decreases towards this local minimum, which would be the equilibrium separation of the two nuclei. And then if you bring the nuclei very close together, then the energy will go up and actually tend to infinity because of the repulsive potential between the two protons that are at the nucleus. So that these different curves represent different states of electronic excitation. And then within this red curve in particular, you see these different lines that represent different states of vibration. Those are the blue lines. And then there's an even finer splitting that's labeled with J, and these green lines that are the various degrees of rotation that the molecule can have. So I'll come back to this in a little more detail later. But one thing to say is what I've just told you really makes use of a key approximation that is always used for understanding molecules, called the Born-Oppenheimer approximation. And the key point of this approximation is that to very good approximation, we can consider the motion of the electrons in a molecule separately from our consideration of the motions of the nuclei. And the reason for this is that, well, both the electrons and the nuclei have more or less the same momentum. That's just going to be of order h bar, that's Planck's constant divided by 2 pi, divided by the size of the molecule. I put in the Bohr radius here. So that would be the same regardless of whether it's a nucleus or an electron. But because the electrons are thousands of times less massive than the nuclei, they then, for a given momentum, will be moving thousands of times faster. So if the nucleus was just a hydrogen nucleus, this factor would be 1837. But if I had a heavier nuclei, it could easily be more than 10 to the 4. So the electrons are moving very quickly. They respond very quickly to any change in the position of the nuclei. And the other thing is that the electron kinetic energies will also be larger by the same factor of several thousand to 100,000. So what this means is that we can initially neglect the kinetic energy of the nuclei and just assume that the electronic wave function and kinetic energy respond instantly to slowly changing nuclear positions. So we could imagine constructing the curves that were shown on the last slide, shown again here smaller, simply by imagining two fixed protons at a series of different separations and ask what would the electronic states be if we solved the Schrödinger equation for that potential with those two protons at that separation. So this underlies everything that we do really in molecular physics. I now wanted to say a little bit about the characteristic length scales that quantum mechanics tells us molecules have, and the different energy scales that we get for electronic transitions, vibrational transitions, and rotational transitions, which it turns out are simply set by the mass ratio for the ratio of the nuclear mass to the electronic mass. So the characteristic length scale for any atom or molecule is basically set by this combination of fundamental constants that is known as the Bohr radius. So it's h bar squared over the mass of the electron times the charge on the electron squared. And this comes out to 53 picometers. And if you remember your undergraduate quantum mechanics, well, the ground state of atomic hydrogen basically has a wave function that is just a decaying exponential with distance from the nucleus. And the length scale in that is the Bohr radius. So the wave function is e to the minus little r, the distance from the nucleus, over a0, the Bohr radius. And with that Bohr radius, then, there's a characteristic energy for electrons. It's basically of order the potential energy of an electron at 1 Bohr radius from a proton. There's actually a factor of a half that comes in, but this is the energy of electrons typically in atoms. I mean, it's a negative energy because they're bound. It's the energy in atoms and also in molecules. And I've written it various different ways in terms of the fundamental constants. And in electron volts, which we often use, it's 13.6 electron volts. So if we have an electronic transition of a molecule, the typical energies are of order this combination of fundamental constants, which we call the Rydberg. It's of order a Rydberg or a little less, but it's typically a few electron volts. And so if you have a transition emitting a photon of a few electron volts, that'll be either in the optical region or the ultraviolet, with wavelengths of between maybe a tenth to a few tenths of a micron. In fact, the first three molecules ever detected in the interstellar gas have optical electronic transitions. They're CH, CH+, and CN, the cyanogen radical, that were detected in the 1930s, actually. And then there are many molecules that have ultraviolet transitions, including H2, OH, water, carbon monoxide, and so forth. So that's the energy scale of electronic transitions. Let's now think about rotational transitions. So suppose we're in a given electronic state, but the molecule starts to rotate. Well, we can write down a classical expression for the rotational kinetic energy of an object with a moment of inertia I that has an angular momentum L. And the answer is L squared over 2I. That's from freshman physics. And L squared is quantized in this way. L squared is j plus 1 h bar squared, where j is any integer. And the moment of inertia is basically going to be the separation of the two nuclei times the mass, or strictly the reduced mass of the two nuclei, which would be the product of their masses divided by the sum. And so if we substitute these expressions into the expression for kinetic energy, what we find when we put in these order of magnitude estimates that I had previously for the characteristic length scale and the characteristic energy of electronic transitions, we find that the rotational energy for a transition from some state J to the next lower state with one less quantum of angular momentum is less than the energy of the electronic transitions by a simple factor of the electronic mass to the nuclear mass. So this ratio is of order 10 to the minus 4. So for that reason then, rotational transitions typically give us photons with photon energies 4 orders of magnitude less than the energies of the electronic transitions that we can observe in the optical and ultraviolet. So a few 10 to the minus 4 electron volts. And these lie in the submillimeter region at a few millimeters in wavelength, as opposed to a few tenths of a micron for the electronic transitions. Now, I did this calculation assuming that my nucleus was a heavy element nucleus containing two heavy element nuclei like carbon monoxide. But actually, if I just have one heavy element nucleus, then this reduced mass is only a few thousand times that of the electron. And so there's only 3 orders of magnitude difference. My photon energy will be a few 10 to the minus 3 eV. And my wavelength is typically one, I really should have this in parentheses, 100 to a few hundred microns. And that's in the far infrared and submillimeter region, which is often blocked from the ground, actually because our atmosphere has many hydrides, including water, well, one important hydride, I should say, water, that blocks this radiation. And if we went to 2 heavy element nuclei, to H2, in fact, the rotational transitions move into the mid-infrared, where actually they're a prime target for X's. Part of the reason is that for H2, the rotational quantum number has to change by 2. And so the lowest transition is at 28 microns, and all of the other rotational transitions of H2 are at shorter wavelengths. So they form squarely in the region axes. And then the third possibility is vibration. And so molecules, in addition to having electronic excitation and being able to rotate, they can vibrate. And for a diatomic molecule, there's only one vibrational mode, stretching mode. And the energy basically is quantized, and it's some integer plus 1/2 times the energy for the classical frequency of oscillation, which I've written as an angular frequency here, omega c. So if you, in the classical theory of a simple harmonic oscillator, this is basically just the square root of the spring constant divided by the reduced mass of the oscillator. And if we went back to that potential energy curve, you can see it's related to the curvature of the potential energy curve that I showed you earlier. That really tells us the spring constant, because close to the equilibrium separation between the nuclei, it'll be roughly quadratic of the form 1/2 k times the displacement away from continuum squared. So if you look at that a little more carefully, you can say then that the spring constant order of magnitude, well, it's going to be the characteristic energy scale divided by the characteristic radius or size scale. So the Rydberg divided by the square of the Bohr radius, you can put that in fundamental constants. Sorry, this should be m sub e, the electron mass, not m times e. And then if you put that in and go through the math, I won't do it in great detail, but you end up with the typical energy of a vibrational transition being the energy for an electronic transition now times the mass ratio to the 1/2 power. So you can verify afterwards that this is all right. So basically now we're moving in between the optical and ultraviolet, where we see electronic transitions, and the radio and millimeter region, where we're seeing rotational transitions. Really into the mid-infrared is where we see the vibrational transitions. So this would be now 2 orders of magnitude below the energy of electronic transitions, an energy of a few 10⁻²⁰ eV, and so in the mid-infrared part of the spectrum, at a few microns. So here's the summary. There's really a hierarchy of energy splittings that is set by the proton to electron mass ratio, really, and it's shown here. And so at the lowest energy range, we have pure rotational transitions where the vibrational and electronic states remain the same. And so some classic examples are the carbon monoxide line from the first excited rotational state to the ground state. That can be observed from the ground, and it's at 2.6 millimeters. If we go to higher lying rotational states of carbon monoxide, the energies of the photons get larger and larger. And so one classic transition that was widely observed with great was the transition from 16 to 15. That's at 163 microns. And then in the X's region, there have been many observations of rotational transitions, for example, from J = 3 to 2 at 17 microns, 5 to 3 at 12 microns. I'll talk about them a little later. And next up in energy, we have rho vibrational transitions in which both the vibrational and rotational state change, but the electronic state does not. And I've given some examples of vibrational bands that have been observed with X's that will be discussed later. And then we have electronic transitions, which are not really targets for SOFIA. Classic examples of these are the bands of molecular hydrogen in the vacuum ultraviolet that were observed with Copernicus and FUSE. So I'll just return to this figure, which hopefully now makes a little more sense. So transitions within the ground vibrational state between states of different J are pure rotational transitions, we call them. They're in the mid-infrared. Then there's rho vibrational transitions where the vibrational excitation changes. And in general, the rotation does as well. And those will be in the near infrared. and then the electronic transitions from one of these curves to another, and that's in the optical and ultraviolet. I want to finish this second section of the course by saying a little bit about the nomenclature and notation, just so that you've seen it. Actually, I think I may miss this. So you'll have these notes and you can refer to this later, but I'll explain the sort of coding that you see on some of these electronic states. I'll also explain some notation that's used to describe how the rotational quantum number changes. And you can look at that in my notes later. And then I had a few other comments that I'll make briefly, that in polyatomic molecules, things get more complicated for rotation and vibration. In general, you can have multiple principal axes about which the moment of inertia is different for each axis. So in that case, then the energy of the molecule that it has by virtue of its rotation depends both on the total angular momentum, but also how it is projected onto the different principal axes of the molecule. And then the other thing is that you can have multiple vibrational modes. So whereas in a diatomic molecule, there's just a stretching of the two atoms, with a triatomic molecule, you could have stretching, but also bending. So there are multiple vibrational modes that will show up as different bands of multiple lines in the mid-infrared. This slide, which you can look at in greater detail as well, talks about the isotopic shifts, the fact that if you put in a different isotope of one of the atoms in a molecule, you'll shift the frequency of the transitions a lot, whereas you only shift it by a few parts in 10 to the minus 4 at most in the case of atoms. And this is because it's the nuclear motions that are important here for vibration or rotation. So the nuclear mass enters. And this can be very useful in two ways. If we think that we have some molecule where the ratio of one isotope variant or isotopologue to the other is reflective of the true elemental isotopic ratio, then we could use it to probe how the different stable isotopes of an element vary in the galaxy. That could give us clues to the nuclear synthetic history, because different types of stars produce different isotopes. On the other hand, there are some molecules, particularly when we're talking about deuterium, where there's a big difference in the tendency of deuterium to be found in that molecule as compared to hydrogen. And then this phenomenon is called fractionation, where the deuterated version of the molecule is slightly more stable and can be more abundant. And in that case, the ratio of deuterated molecules to ordinary hydrogen-bearing molecules can be used as a useful probe of astrochemistry. Perhaps we can assume that we roughly know the elemental abundance of deuterium. And then the final point is that I wanted to add is that for some molecules, the nuclei have spin. So many of the most abundant elements don't actually have any spin. They're so-called alpha nuclei, where we have an even number of neutrons, and that's equal to the number of protons. And these, I believe, without exception, are spinless. So they don't give rise to any of the complications that I'm about to mention. But there are many abundant nuclei do have non-zero spin, most notably hydrogen, which is just a proton, so it has spin 1/2. Other abundant nuclei are nitrogen-14, which has spin 1. Carbon-13 has spin 1/2. I've listed others here. If there is a non-zero nuclear spin, and also there's a net electronic spin, then there can be an interaction between the two because they both act as little magnets that can slightly split the energy states. And this is called hyperfine splitting. And we see it a lot in rotational spectra. In vibrational spectra, the splitting is typically too small to be detected. So this is generally negligible at the wavelengths and resolving power of X's. But one important thing that I'll come to near the end of my talk is that if we have 2 or more identical hydrogen nuclei, then the total nuclear spin, the vector sum of those 2 nuclear spins, has to be correlated with the rotational state. And this has profound effects and gives rise really to 2 different forms of the molecule that we call ortho and para forms. And I'll discuss that in a little bit. So the final 2 slides in this second part of today's talk are just a couple of references for good places to find the molecular data that you need to interpret molecular spectra. And for wavelengths and transition rates, the rates at which we get spontaneous radiative decay from an excited state to a lower state, there are 2 resources that I use most often. One is the HYTRAN database, which is mainly for molecules that are found in Earth's atmosphere. And then there's ExoMol, which has a larger set of molecules and is motivated by exoplanets. And these have very large line lists for simple molecules. If you need to know the rate at which molecules might be excited as a result of collisions, then here are 2 other databases, BaseCol and Lambda, that is maintained at Leiden, that have compilations online of the data that you need. Finally, I'll leave you with some further reading on molecular spectroscopy. So there's a simpler but very good summary in Bruce Drain's book, Physics of the Interstellar and Intergalactic Medium, in chapter 5, that is sort of 15 pages. But if you can't find it there, then you'll need to go to the Bible of molecular spectroscopy, which I would really recommend this book, Microwave Spectroscopy by Towns and Charlow. Okay, so that brings me to the end of sort of the fundamentals of molecular spectroscopy. So maybe if there are some questions in chat, I could answer those, Lars, or if not, just tell me to go on.
At the moment, there are no questions in chat. Maybe we pause for a little bit to see if there's any questions, but maybe raise your hand if you have a question regarding this section. That would be potentially quicker than using the chat. I see no raised hands.
Okay, so I'll move on then. Okay. So I had a table basically to summarize the instrumentation we have for astronomy in the mid-infrared region, which I'll somewhat arbitrarily define as the region from 3 to 30 microns. And I'm talking here now about spectroscopy. So I've listed things, various different observatories and instruments in the leftmost column. So the short wavelength spectrometer on ISO was really a very key instrument that flew more than 2 decades ago now, and provided pretty high resolution spectroscopy throughout the mid-infrared region. There was also Spitzer, which had much lower resolution spectroscopy in the mid-infrared. And then, of course, SOFIA Xes, which covers the 5 to 28 micron spectral region at a higher spectral resolution than any of these other instruments. So what I'm showing you in the third from left column is the typical resolving power, as it's known, ratio of lambda to delta lambda, the resolution, which for Xes can be as high as 10 to the 5. And this uses a different technology from either the short wavelength spectrometer or the infrared spectrograph. It's a cross-dispersed Echelle spectrometer that I'll explain in a minute. The other columns that you see here, and you could refer to later, are what I call the spatial multiplex advantage, which really means the number of positions on the sky that you can observe at the same time. And then there's the diameter of the primary mirror of the observatory in meters. So that's sort of the 3 workhorse instruments that we've had until very recently in space or suborbital. Of course, with James Webb now, we have MIRI and NIRSPEC that cover different parts of this mid-infrared region. They're very sensitive. They have a very high spatial multiplex advantage because they have what's called an integral field unit, IFU, where you can get individual spectra simultaneously at a grid of positions that is 30 by 30. It's a large primary mirror, so it gives you very good spatial resolution, but it does not have particularly good spectral resolution by comparison to Xes. So it's really in the respect of spectral resolution that Xes really provides a unique capability. And then there are parts of the mid-infrared spectral region that can be observed from the ground, and I've listed some instruments on different telescopes, all of which have high resolution spectroscopy, some of which have a pretty nice spatial multiplex advantage, and which are on large telescopes, even larger than Webb in certain cases. But of course, the key problem or shortcoming of these is that large parts of the spectral region are blocked by the atmosphere, and there are small windows where one can observe from the ground. So the rule of thumb is that if you are looking at a wavelength that can be observed from the ground, you should always observe from the ground because you'll have a larger telescope and it's a less precious resource. But throughout most of this region, you really have to go at least to suborbital altitude. I've contrasted the different ways that these instruments use two-dimensional detectors to get a combination of spectral and spatial multiplexing. So you have long slit spectrographs like Spitzer that disperse in one direction, and then in the other direction, you get the spatial variation along the slit. I mentioned the integral field units that are used on Webb, and the cross-dispersed Echelle that is used on Xes, where light is basically dispersed at very high resolution in one direction, And then there are multiple orders of the spectrograph that are separated in the other direction. So you get these bands where wavelength sort of follows a zigzag pattern across this two-dimensional detector. And then you'll see each band has a finite width, and that's telling you spatial variations along the slit. Now, this is just the spectrum of the sky, so there is no spatial variation. And you're just seeing each dark line here is an atmospheric absorption line in the spectrum of a background star. I'm sorry. Well, these are probably emission lines, actually. Yeah. So this is, well, I don't quite know what this is, but it's these dark lines are either absorption. They must be absorption lines. Okay, so that's sort of a brief summary of the instrumentation. I can see that I'm running out of time here, and I wanted to discuss two examples, but actually I know that Sarah Nicholson will sort of touch on one example or something related to the second example I was going to give, which is vibrational absorption that has been observed with XEs. So I'm actually going to just focus on the other key molecular application, which is rotational transitions of molecular hydrogen that has proved an important target for XEs. And I'm going to describe some observations that have been carried out of molecular hydrogen in interstellar clouds that have been heated up by shock waves, where supersonic motions, outflows from a forming protostar, have impacted the surrounding gas and heated it to temperatures of several hundreds to thousands of Kelvin. We can then see the rotational emissions that are excited in that gas. So this is the rotational diagram for molecular hydrogen. And the selection rules for molecular hydrogen, which doesn't have a dipole moment, are that the rotational quantum number has to decrease by 2. And that's called an S transition. So we have S0 from 2 to 0, S1 from 3 to 1, S2 from 4 to 2 at successively shorter wavelengths within the XEs band. But it's a little bit more subtle than just the fact that H2 doesn't have a dipole moment. And the little subtlety of quantum mechanics is that the hydrogen nuclei are two identical fermions with spin 1/2. And quantum mechanics tells us then that the wave function of this molecule must be antisymmetric with respect to the interchange of those two fermions. It's true of any pair of fermions in the universe. And so if the spins of the nuclei are parallel, so that they add up to give a total spin of 1, then the rotational part of the wave function must be antisymmetric in order for the overall wave function to be antisymmetric. And that means that the rotational quantum number has to be odd, and we call that ortho H2. On the other hand, if the total spin is 0, meaning that the spins of the two hydrogen nuclei are antiparallel, then in order for the overall wave function to be antisymmetric, the rotational part must be symmetric, and J has to be even. So one can really think of having two separate molecules, one with odd J states and one with even J states. And we call these ortho and para hydrogen, because para hydrogen has the J equals 0 state, then it will actually be the lower energy form of H2. And so in equilibrium, the ortho to para ratio is 0 for very low temperatures, because everything will be in the ground rotational state, and that's para-hydrogen. But then will tend to 3 in the high temperature limit, because then we'll have many rotational states, and all the odd rotational states have a higher degeneracy because they have total nuclear spin 1. They have a degeneracy of 3 rather than 1. So the orthopara ratio will be 3. So there are really 2 different types of hydrogen molecule, and the conversion between them is extremely slow. It's forbidden by radiative transitions. And even in an inelastic collision, the chance of changing from an odd J state to an even or vice versa is negligibly slow, because basically you would have to change the rotational state of the molecule at the same time as you flip the spin of one of the nuclei. And that's on very different scales and negligibly probable to happen in a collision. So really, the conversion of ortho to para hydrogen or vice versa is very slow and lags behind the temperature. And this is well known actually in the industrial production and storage of liquid hydrogen. You might think it'd be very easy to make liquid hydrogen. You would just cool down hydrogen gas. But if you just do that, you find that the liquid hydrogen you produce has an ortho to para ratio that is frozen in at the high room temperature value, which would be 3, even though in equilibrium at the temperature of liquid hydrogen below 20 Kelvin, the ortho to para ratio would only be 0.01. This is actually a problem, because if you just cool down liquid hydrogen what you will find is that you'll have liquid hydrogen with an ortho para ratio of 3, and it'll very slowly find its or move towards equilibrium with ortho converting to para. And the timescale for doing this is 6.5 days. And it releases heat as this happens. In fact, it releases more heat than the latent heat of vaporization. So if you just put it in a dewar, it would all boil away. So the way they get around this is they put in a catalyst that it's a paramagnetic salt that promotes the conversion of ortho to para hydrogen. Well, amazingly, we see the same effects, sort of the other way around, in astrophysical H2, where we first saw this with the Infrared Space Observatory. We see that the ortho to para ratio is actually less than 3, even though the temperature of the gas is quite hot. And the way we can represent the relative strengths of the different transitions of, or the different states of molecular hydrogen, is with a rotational diagram, where we plot on a linear scale. On the x-axis, we show the energy of the upper state, and on a logarithmic scale, we show the number of molecules to be found in the upper state of each transition, divided by the degeneracy of the molecule. And in thermal equilibrium, all the points would lie on a straight line with a slope that would tell us the temperature of the gas, because it's all based on the Boltzmann factor, where the number of atoms in any given state or molecules is the degeneracy times E to the minus energy over kT. So if we plot energy versus the log of the number, we would get a straight line in equilibrium. And what you see is this zigzag behavior, where all the even J states, the states of para H2, lie above those of ortho H2. So the slope tells us this gas is at 650 Kelvin, but they're not on a straight line. So the ortho to para ratio is actually less than 3. It's about 1.2. which is the value it would have in equilibrium at 90 Kelvin. And so the explanation of this is we're really seeing a fossil, if you like, of a period when the gas was cooler than it is when we see it. So the gas cooled down, its author-power ratio approached equilibrium. It was then heated temporarily by a shock wave to 650 Kelvin, but the author-power ratio hasn't had time to catch up. It hasn't had time to reach equilibrium. So this tells us that the heating must have been temporary. And this is consistent with the idea of a shock wave propagating through the gas, heating it up for a little while, and then it cools down. We saw this again with Spitzer, with now more rotational states. We could fit these rotational lines with a model for these shocks where we include the conversion from para to ortho H2 as the gas has heated up. One thing you may notice is that there's more of a zigzag for the lower energy transitions than there is for the higher energy transitions. And what this means is that hotter components of the gas, which are preferentially giving us the higher lying rotational states, have been more successful in their advance towards equilibrium in the author-power ratio than have the cooler parts of the gas. And this is understood in terms of detailed models. So this then raises the question, could we actually see para-hydrogen being converted to author hydrogen within a shock? And the linear scale for this in the best models we currently have for shocks is pretty small. It would be certainly less than an arc second, even for the closer sources. So maybe you could see that with Webb, but certainly it couldn't be detected with any previous infrared observatory. But there's another way of getting at this if you have high spectral resolution. And the reason is shown by this diagram, which shows you how in an interstellar shock of the type that we think we have in the clouds that we're observing, a so-called C-type shock, the velocity of the gas, this Vn is the velocity of the neutral component of the gas, is smoothly varying from, it starts out at 25 kilometers per second in this model, and is gradually reducing as we move through the shock, which is shown on the coordinate here on the x-axis. So the gas is heated up and remains hot for a fairly long period. The gas changes its velocity as time goes on. And also the author-to-para ratio increases as ortho-hydrogen is slowly converted to para-hydrogen. Well, an implication of this is that you might expect to see a shift then in velocity between the transitions of even J that trace the para-hydrogen and those of odd J. And in fact, just such a prediction was made. This is with the Paris-Dunham shock code run here by Pierre Le Saffre. And you can see his model predicts a shift between the even rotational quantum number states, so transitions. So this is S4, J equals 6 to 4, and S6, J equals 8 to 6. Those are all shifted by a few kilometers per second relative to the odd J states. So we looked for this in mid-October of 2018. We observed these 4 transitions, 2 of para water, 2 of para H2, 2 of ortho H2 within this famous shock the Herbig-Haro objects HH7, where there's some protostar over here on the upper right, and there's a jet that impacts the ambient gas down here and shocks the H2. And we used XEs to observe this with actually 2 positions. So this is just a finder chart superposing this on maps of the vibrational emission in black from H2. And this is what we saw with the high resolution of XEs. This is completely XEs unique. And you can clearly see a beautiful agreement with what is expected with this systematic shift of S5 and S7 relative to S4 and S6. Here's the velocity centroid plotted for these different transitions. So there's a few kilometer per second shift. And we can sort of plot then how the author to power ratio increases with decreasing velocity. This is basically as the gas is flowing through the shock. So we would say we're tracking the author power conversion through the shock. And what we've really shown with this then is that the flow velocity is changing gradually. It doesn't jump suddenly at the shock front as it would in a different class of interstellar shock. There's a special class of shocks that are predicted to be important in shocks that propagate through molecular gas that are not too fast. That was first introduced by Bruce Drain. They're called C-type shocks. And the C here means that the velocity of the gas, the flow velocity, varies continuously, as opposed to a J-type shock where it would jump. And this continuous variation then is supported, really, I would say, proved perhaps for the first time by these XEs observations of the pure rotational states of H2. Okay, well, I'm going to apologize for having timed pretty poorly what I had planned to say. Sometimes this goes quickly and sometimes, I don't know, I speak more slowly and with more parenthetical things that I felt I needed to say right then. So I apologize for that. I missed one of the 2 applications. You can read it later, but as I said, I think Sarah Nickerson will talk quite a bit about the vibrational lines that XEs can observe. So I think it's fine to for me to have missed that. And then the details of molecular spectroscopy that I had to skim over, you'll be able to find in my notes, which are already posted on the website. So sorry about that. And now I'm happy to take questions for the remaining 20 minutes, or maybe you just want to have a break yourself. Anyway, I'll be here.
Oh, thank you very much, Dave. It was a very, very good talk. So for me, it was no problem. You went a couple of minutes over time. It's very educational. I noticed there were 2 comments, at least in the chat. Maybe let's start out with those. So there was Bernard Schultz, who mentioned that one remark, ISO also has had isopods S at a 2.5 to 12 micrometer spectrometer at R equals 100, and the variable filter on ISOCOM.
Yes.
And then there was also Curtis, who commented on the XEs figure that you showed. So these are the dark lanes are in the slide were ozone and carbon dioxide sky lines seen before sky subtraction.
Right. So then he's saying they're emission lines, which actually I guess they have to be, because otherwise there would have to be a uniform background. So I guess it's a sort of reversed scale. The darker parts are where the detector has received the most photons. So these are all emission lines. And that's right. I mean, a big complication in this spectral region, even at airborne altitude, is the significant emission from the sky and also absorption. So that if you, presumably, it would be hard to observe astronomical emission in the depths of some of these broader features. So this is around 13 microns.
Are there any other questions? Feel free to type in chat or raise your hand. Well, maybe I'll start with a minor question myself. When you were showing the C-shocks, it was, I think I forgot the timescale evolution of a C-type shock. So because you plot as a function of distance, I presume that the timescale for a C-type shock is a few days based on the need for the ortho-to-para ratio to change.
Well, no. So this 6.5 days was for liquid hydrogen, in a dewar. So it's a pretty, dense environment. The timescales for ortho-para conversion are much longer at the low densities of these clouds. So the length scale, I would say it's hundreds or thousands of years would be the time taken for the gas to flow through this shock. So it's not days. It's probably 100 years.
Okay. Yeah, thank you. I think I got a little bit confused.
But the ortho-para conversion is correspondingly slower. Right. So in fact, you sort of get partial conversion that the overall or the average ortho-to-para ratio is larger than what it originally was, but has not yet reached 3.
Thank you. I forgot to take the density into account there.
Yeah, right.
I see a hand from PJ.
So a clarification question, David. For the ortho-to-para conversion, if I remember my molecular physics right, it requires a exchange reaction that you have to take one of the nuclei and actually replace it. But you're saying that there is some cross-section for changing the molecule without exchanging the nucleus. Is that correct?
No, I'm not. So in fact, I didn't have time to focus on this slide, but it's exactly what you said, that you really have to break a bond and have what's called a reactive collision. So this isn't just an ordinary inelastic collision. It's a collision where you had a para H2 molecule, and in fact, it would be hydrogen atoms that dominate this process. And you actually break a bond so that one of the hydrogen nuclei in the original molecule is replaced by a different hydrogen atom. And that's partly why it's so slow. First of all, this gas is mainly molecular, so you don't have very many hydrogen atoms. And also, even if you do have a hydrogen atom, you have to put in a little bit of energy before you can have this reaction. So it's what chemists would call an activation energy barrier, where even if you have a reaction that is exothermic, which would be the reverse reaction, you still have to have a significant kinetic energy just to get the reaction going, because you have to break this bond. And it corresponds to a temperature of about 4,000 Kelvin. So there's going to be some exponential factor, exponential dependence on the temperature for how quickly the ortho-para conversion can occur by these reactive collisions. And that's actually why the faster shocks get closer to equilibrium. So if you look at this rotational diagram, in addition to the zigzag, you can see it's sort of curved. That means there's a mixture of temperatures present within the beam. Maybe there's some shocks are going a little bit faster, giving us hotter gas, some a little bit slower, giving us cooler gas. And in the faster shocks, which are the ones that we're really looking at with the higher lying transitions, we get less zigzag. We've come closer to equilibrium because in the faster shocks, well, first of all, we destroyed a little bit more of the molecular hydrogen to make free atomic hydrogen that can cause author to para conversion. And also those faster shocks are hotter. So once we have the hydrogen atoms, a higher fraction will have enough kinetic energy to undergo this author-para conversion reaction.
Thank you, David. That was one of those aha moments. That was great. Thank you.
At the moment, I see no further questions. Maybe people are on getting on their break.
Yeah, I can imagine after such a long talk, people will want to take a little break. I mean, I should say, I don't know if my email is posted anywhere, but if questions occur to people later, I'd be more than happy to answer them via email.
Yeah, what could be option is potentially that we add it in the chat.
Yeah.
People are interested. Well, there you go.
I'll put it here.
Yeah, and I will post that version. That's great. Thanks, David.
Okay.
That's very helpful.